Welcome everyone to the second lecture of Chapter 22, the respiratory system. This lecture we're going to be looking at the mechanics of breathing, the how we breathe and why air moves in and out of our lungs. And also we're going to be looking at some properties of gases and talking a little bit more about physics. But before we get going, let's talk about our not really attendance questions for the day. While sitting watching TV relaxing, your respiratory rate is typically around 12 breaths per minute. Which center is most responsible for this? And second, container A is connected to container B by a hose. Container A holds a gas at a pressure of 800 mmHg, and container B holds a gas with a pressure of 485 mmHg. When the hose is opened so that the two have a pathway between them, what will happen to the gas within? So go ahead and try to answer those questions. And now let's see what the answers should be. While sitting watching TV relaxing, your respiratory rate's typically around 12 breaths per minute. Which center is most responsible for this? Well, if you are at rest, then you're not really needing an increased amount of oxygen. You are just at your basal rate. And that is when the VRG is most in control. Now, it might be even getting slowed down a little more than that, depending on various factors. So if it is getting slowed down even more, then the DRG would be in control. But we are just saying, without any outside influence, what's going on. And here, it's your VRG that is setting your respiratory rhythm. Container A is connected to container B by a hose. Container A holds a gas at a pressure of 800 mmHg. Container B holds a gas with a pressure of 485 mmHg. And when this hose is opened, what will happen to the gases within? Well, the pressure difference is going to cause diffusion of gases. Remember, gases will move from an area of high pressure to low pressure, just like solutes will move from high concentration to low concentration. So gas will move from container A towards container B until equilibrium is reached. Don't forget that lymphatic is self-study. I do ask that you read the lymphatic system prior to watching the lectures of the immune system, because the immune system is going to rely on you knowing some of the material that you will learn in the lymphatic portion. So let's go ahead and get rolling with the mechanics of breathing. And this picture is on page 864 of your textbook. And some students really like this picture. I don't much care for this picture. So I'm going to draw this out step by step, because I don't think that this really fully explains everything that we need to look at. So I'm going to exit out of this and get to the whiteboard, and we're going to draw the mechanics of breathing and what happens with the muscles, with the pressures, everything involved with breathing here. So first, let's draw someone's thoracic cage, their rib cage, and their diaphragm, and the lungs within. And while you're drawing this, I'll explain kind of what you're looking at here. What I've drawn is in black. This is the trachea going down towards the lungs, and that's what we have down here. The red is the rib cage and the diaphragm. So this area right here is inside the lungs. This is the intrapulmonary space. And then here, inside the rib cage, but outside the lungs, this is the intrapleural space. And of course, out here, this would be the atmosphere. So let's go ahead and put our pressures in. Hopefully everyone remembers the pressures. Let's say right now we are at the end of an exhale. We're getting ready to inhale, but right now we're at the end of an exhale. So what is atmospheric pressure? It is 760 mmHg. Those are M's. And inside the lungs, at the end of an exhale, is also 760 mmHg. And that's the intrapulmonary space. Then in here, inside the rib cage, but outside the lungs, so the intrapleural space, what's the pressure there? It's about 756. Remember, it's about 4 less than what is in the intrapulmonary space. So there's our pressure. Let me go ahead and put our units here. mmHg. We're going to inhale. And as we inhale, we're going to see everything that changes during this inhale. So during the inhale, first, we're going to contract some muscles. We're going to first look at the diaphragm. The diaphragm contracts and it moves down. It moves inferiorly. The diaphragm contracts and moves down. Now, in between our ribs, there are a few different types of muscles. During inspiration, we're going to look at what happens to the external intercostals. The external intercostals contract, and that causes the ribs to move up and out. The diaphragm contracts and moves down. The external intercostals contract, the ribs move upward and outward. So try to picture this using your own chest. If your diaphragm moves down, so the muscle that runs right below your ribs, if it moves down, and if your ribs move upward and outward, what's going to happen to this area right here? What's going to happen to the intrapleural space? Is it going to get bigger or is it going to get smaller? Well, it's going to expand, so it's going to have increased volume. I'm going to go ahead and write that over here. There's an increase in volume. But think back to last lecture. If there is an increase in volume, what happens to the pressure? Well, exactly the opposite. When volume goes up, pressure goes down. So as the intrapleural space has an increase in volume, there is a decrease in pressure. And if there is a decrease in pressure, it doesn't matter how far it decreases. Let's just take this 756 and give a number to it. Let's just call it, let me erase this right here. It goes from 756 downward. So let's say it goes to 752. All right, now that's not a number that's set in stone. That's just showing that it went downward from 756. Now, if this pressure here drops lower than it was, that means that transpulmonary pressure has an increase in magnitude. And what did we say happens when transpulmonary pressure is greater? What does it do? It pulls on the lungs. So when the intrapleural pressure drops, it pulls on the lungs. It creates a vacuum, so it pulls on the lungs. And when we pull on the lungs, think of this as a rubber band. If we pull on them, then what's going to happen? It's going to cause an increase in the intrapulmonary space. It's going to cause the lungs to get bigger. So the volume is going to increase. And if the volume of the lungs increases, if the volume of the intrapulmonary space increases, what happens to the pressure inside the lungs? If volume goes up, that means pressure goes down. Now, it doesn't matter how far it goes down. It's just going to go down to less than 760. So let's go ahead and drop this number to less than 760. Let's say it drops down to 756. Now, pressure at this point in the lungs is less than atmospheric pressure. Out here in the atmosphere, remember, it's 760. In here in the lungs, it's 756. So now there's a difference in pressure, and there's an available path between them. Now, in my in-person class, I make this big dramatic show. I lean my head back and I open my mouth wide and I say, if you had me for Bio 137, you probably heard me say that the inside the lungs are really outside the body. There's not really anything physical in between the inside of the lungs and the outside of the body. It's exposed to the atmosphere. So inside the lungs is exposed to the atmosphere. There's a difference in pressure and an available path between them. That sets up exactly what we opened with. What happens? Well, air is going to move in from the air around you in the atmosphere into your lungs. So air moves in until the pressure inside the lungs is equal to atmospheric pressure. So we dropped it to 756. Air continues to move into the lungs, and this is going to rise until it gets back to 760. Once it gets to 760, we are at the end of an exhale. So everyone take a deep breath real quick. Just inhale. At some point, you stop inhaling, don't you? Why do you stop inhaling? Because the pressure in your lungs is equal to the pressure in the room around you. All right, so now I'm going to clear most of this out. Actually, I'm just going to redraw the whole thing. And we are now at the end of an inhale, and we're going to look at how we exhale. I'm not going to put the units here. Always put the units, but I'm not going to just because you already know what the units are since this is technically the same drawing. We were at 752 at the end of that last drawing. Now we're going to exhale. Now during exhale, we're not going to contract anything. Inhaling, we contracted. Inhaling was an active process. But exhaling, we're going to be relaxing a bunch of muscles. Exhaling is a passive process. Inhaling takes energy. Exhaling does not. So during an exhale, during expiration, the diaphragm relaxes and it moves upward. The external intercostals relax. The ribs move inward and downward. So this is all exactly the opposite of what we just saw. So as the diaphragm moves upward, as the external intercostals relax and the ribs move inward and downward, the intrapleural space, what happens? It gets smaller. So there is a decrease in the volume of the intrapleural space. And as the volume goes down, the pressure goes up. Now it doesn't matter how far it goes up, it just goes from 752 upward. So we're just going to take it back to what it was in the very beginning, and we're going to say it gets back to about 756. So if it was 752 and now it's 756, is it pulling on the lungs harder or softer? Well, now it's pulling on the lungs softer because the transpulmonary pressure has less magnitude. There's a smaller difference between 760 and 756 than there was between 760 and 752. Okay, so when we get up to about 756, we are pulling on the lungs less. We're not pulling on the lungs as hard. So that stops pulling on the lungs, which causes a decrease in the intrapulmonary space because the lungs, remember, they're elastic and they have that surface tension. So the lungs naturally will snap back like a rubber band. So the volume in the intrapulmonary space is going to decrease. So what's going to happen to pressure in the intrapulmonary space inside the lungs? It's going to go up. And it doesn't matter how far it goes up. It's just going to go up above 760. And if it goes up above 760, let's just give it a number. Let's just call it 762. If it goes up above 760, now the pressure in the intrapulmonary space is greater than atmospheric pressure. Again, difference in pressures, available pathway. Air is going to rush out of the lungs. How long does it rush out? Until it is equal to atmospheric pressure. So as air is moving out, this 762 is dropping. And it continues to drop until it gets back to 760. Once it gets to 760, air stops moving out. So real quick, everyone, take a breath and then let that air out. You don't breathe out forever. Air stops moving out at some point, and that point is when it is equal to 760. So that's kind of what this picture is showing. If this picture makes more sense than the drawing we just did, use this picture. But I personally think that drawing that we just did shows a little bit more of the mechanics. But even though inspiration is an active process that uses energy to contract muscles, and expiration is a passive process that does not use energy because muscles are relaxing, that's during quiet respiration. Remember, just the respiration when you're not paying attention to it, when it just happens naturally on its own. But sometimes there are some other times that we breathe differently. For example, forced expiration, which is what we see in this picture here. Forced expiration is like when you're blowing up a balloon or playing a musical instrument like a woodwind or something, and you're, forcing the air out. The little girl here blowing out her birthday candles. In this case, expiration becomes an active process. We're going to contract some muscles to force air out. And it's going to be a different group of muscles than we use during quiet respiration. It's going to be another set of those muscles in between the ribs, but these are the internal intercostals. And we're also going to use the abdominals. So the internal intercostals and the abdominals contract to cause forced expiration, as when you're blowing out a candle or blowing up a balloon. Now, I also want to talk about lung compliance. Lung compliance is the ability of lungs to expand. We need lungs to be able to expand really, really easily, because when we breathe in, we don't want any resistance to those lungs as they get bigger, as they fill with air. We want the lungs to be able to expand really, really easily. Now, some things can interfere with that. So we say that it causes a decrease in lung compliance. Things like scar tissue from smoking or COPD. Anything that interferes with the ability of lungs to expand will make it harder to breathe. We say that it reduces lung compliance. The higher the lung compliance, the easier the lungs expand, the easier it is to breathe. The lower the lung compliance, the harder it is for lungs to expand and the harder it is to breathe. So let's talk about a couple of disorders. First is asthma. Asthma, which is what we see illustrated here, there are different types and different causes of asthma, but the result is the same, and that is the really, really small bronchioles deep down in the respiratory tree, the bronchial tree. There's this layer here called the mucosal layer. I'm sorry, the submucosal layer. And in the submucosal layer, typically it's really, really thin. But sometimes something can irritate and cause an inflammation, a swelling. And when that happens, that submucosal layer gets thicker. Now remember the term lumen when we were talking about blood vessels? Lumen is the hollow part of an organ. Well, here, the lumen of the bronchioles, that's where air passes through. If the submucosal layer is to get thicker, what's going to happen to the lumen? It's going to get smaller. And that's what happens during an asthma attack. The lumen gets much smaller. And if the area where air passes through is smaller, there's going to be more resistance. It's going to be much harder to breathe. Now, I've never had an asthma attack. I don't have asthma. But speaking to people who have, they say things like, it's like breathing through a small straw. And that's because this lumen is so small. Now, this part, not so important for lecture, but just, I know a lot of you are either going into respiratory therapy or nursing, just to give you an idea of what happens if someone is having an asthma attack. Typically what we do is we give them some sort of steroid. Maybe we give them epinephrine, but more likely we're going to give them some sort of steroid like albuterol. And the thing that epinephrine and steroids will have in common is they reduce inflammation. So it's going to have the opposite effect of this. Also, epinephrine, just the sympathetic nervous system in general, has the effect of dilating the bronchioles, making them more open. So, in an asthma attack, epinephrine is just like really activating your sympathetic nervous system. It's going to cause bronchodilation. So now there's a new term. Do not get bronchodilation, the dilation of the bronchioles in the airways. Don't get that confused with vasodilation. Vaso is specific to blood vessels. Here we have bronchoconstriction and bronchodilation. That is different from vasoconstriction and vasodilation. Next, something called IRDS, or Infant Respiratory Distress Syndrome. In this case, most of the time, this affects babies who are premature. Preemies are at risk for IRDS because, well, first let's talk about what IRDS is. Now, remember in the last lecture when we talked about surface tension and surfactant? Well, in IRDS, surfactant production is less than normal. If there's not as much surfactant as we need, then surface tension is more likely to develop. So if surface tension develops around those alveoli, it's going to make it much harder to breathe in because we have to expand against that shell of surface tension. Now, babies, when they're in the womb, they really don't have much need for fully developed lungs. They're not breathing when they're in the womb. They're getting all of their gas exchange through the placenta, through mom's breathing. But right before a baby is born, that's when lungs really start to develop. So if a baby is born premature, depending on how premature, its lungs might not be fully developed, including those type 2 cells. Now, if those type 2 cells are not fully developed, we're not going to see that surfactant getting made. And when this baby exhales and his alveoli deflate, surface tension is going to develop. And then when the baby's going to breathe in again, it's not going to have the ability to exert the effort it would need to reinflate those alveoli. It's going to have a really difficult time inhaling. So almost without fail, when babies are born premature, they're going to be put on a ventilator. And that ventilator is going to force air into their lungs so that they don't have to exert the effort to inflate their lungs. Okay, I apologize if this slide sounds a little distorted. I actually had to record this slide separately because there was an error in the initial recording, and then I've gone back and added this slide in. So what we're seeing here is called a spirograph or a spirographic readout, and this is going to be showing us the different volumes or capacities, basically the different levels of air, the different measurements of air in different types of breathing within the lungs. Now, the numbers here, the actual volumes, we don't need to know that for lecture. I want you to know what each of these names that we're going to be talking about represents. For example, if I ask you about tidal volume, I want you to know what tidal volume means more so than what is the measurement of tidal volume. Now in lab, there are going to be some volumes that you need to know. So there is some overlap here between lecture and lab, and then there are some things that you need to know more for lecture versus more for lab. So let's go ahead and look to see what this is showing us and how we obtain it. Now, up here at the top, this is how we obtain it. There is this device that the patient is breathing into, and it's going to measure the volume of air blown out or breathed in. And then once that's been done, we get a readout that looks like this down here at the bottom. Now, there's different types of breathing, which we can see by the different types and sizes of waves in this readout. Now, when you're just normal, quiet breathing, so that's a phrase that we're going to hear a lot this chapter, normal, quiet breathing, which is just your regular inhale, exhale without really thinking about it. And that's what we see here in this yellow region. So we have our regular inhale and then our regular exhale. And that volume here, represented by the yellow area, is called tidal volume. And tidal volume is just the volume of air either inhaled or exhaled. So it's the volume of air moved in one quiet inhale or one quiet exhale. Tidal volume, normal quiet breathing. The volume of air moved in one tidal inhale, quiet inhale, or one tidal exhale, quiet exhale. Now, let's say you breathe in a normal breath, and then you breathe out a normal breath. So that inhale was a tidal volume inhale. The exhale was a tidal volume exhale. There's still quite a bit of air left in your lungs. So after your normal tidal exhale, starting from that point, let's breathe out more. Let's breathe out as much as we can. So that's this area here in kind of this dark blue area. And this is called the expiratory reserve volume. So the expiratory reserve volume is the volume of air that can be exhaled forcibly after a normal, quiet, or tidal exhale. It does not count the tidal exhale itself. It is only the amount of air that we can exhale forcefully after a normal tidal exhale. So now we see we breathe in again. And now we're back to our normal tidal inhale, tidal exhale. Tidal inhale, tidal exhale. Tidal inhale. So now once we've taken our normal tidal inhale, our lungs are not completely full. We could forcefully inhale quite a bit more. And that's what we see right here. So we've taken our normal tidal inhale, and from this point, we begin measuring. And we inhale as deeply as we can. And that's what this pink area here is showing us. This is called the inspiratory reserve volume. And the inspiratory reserve volume is the amount of air that we can forcefully inhale after a normal tidal or quiet inhale. Now, those are different volumes. When we're talking about capacities are when we add different volumes together. So let's see some different capacities. Let's exhale again. And now we're back to our normal tidal volumes. But let's inhale the normal tidal inhale plus the maximum inhale, so the inspiratory reserve volume. If we measure the tidal inhale plus the inspiratory reserve volume inhale, so the yellow plus the pink, that is called our inspiratory capacity. Inspiratory capacity is tidal volume plus inspiratory reserve volume. I'll say that again. Inspiratory capacity is tidal volume plus inspiratory reserve volume. It includes a regular quiet inhale plus the air that we can forcefully inhale. So right now, we're at the top of an inspiratory reserve volume inhale. Our lungs are maximally inflated. They are as full as we can make them without doing damage. Now from that point, let's say we blow all of the air out that we can possibly blow out. So we've blown out our inspiratory reserve volume, we've blown out our tidal volume, and we blow out our expiratory reserve volume. So that is all of the pink. It is all of the yellow, and it is all of the dark blue. That is called the vital capacity. Now, the vital capacity is going to have a few different definitions. First, it is inspiratory reserve volume plus tidal volume plus expiratory reserve volume. I'll say that again. Vital capacity is inspiratory reserve volume plus tidal volume plus expiratory reserve volume. Now, another way that we can define this vital capacity, it is all of the air that we are capable of moving. So you filled your lungs up as full as you can, and you breathe out as much as you possibly can. During that breathing out, that is blowing off your vital capacity. Now, if we take, let's see, which ones have we covered here? If we breathe out as much as we possibly can, so now our lungs are as deflated as we can make them. We've blown off all of the air that we can blow off. Well, our lungs do not deflate like an empty balloon. When we blow out all of the air that we can possibly blow out, there is still some air left in our lungs that we are unable to breathe out. And that's called it's called residual volume. The residual volume is the volume of air that remains in our lungs after maximum expiration. Residual volume is the volume of air that remains in our lungs after a maximum expiration. So, if we combine the expiratory reserve volume and the residual volume, that gives us functional residual capacity. Expiratory reserve volume plus residual volume is equal to functional residual capacity. So what is functional residual capacity? Functional residual capacity is the volume of air left in our lungs after a normal, tidal, or quiet exhale. So when you're just sitting around and you're breathing and you breathe in and then you breathe out, it includes the air that you could potentially breathe out and the air that you are incapable of breathing out. That is the functional residual capacity. And there's one more volume that we need to know. If we take all of the air that our lungs can hold, so let's say you breathe in as much as you possibly can. So right now, you are at this point. Your lungs are as inflated as you can make them. If we were to measure all of the air that is in your lungs, that is called the that is called the total lung capacity. Total lung capacity is how much air can your lungs hold? And we find that by adding the inspiratory reserve volume, I'll write IRV, plus tidal volume, TV, plus expiratory reserve volume, ERV, plus residual volume, RV. Sum that up. Total lung capacity is the volume of air that your lungs are capable of holding. Both the air that you can breathe out and the air that you cannot breathe out. It includes inspiratory reserve volume, IRV, tidal volume, TV, expiratory reserve volume, ERV, and residual volume, RV. Now, of all of these different volumes and capacities, it is tidal volume, normal, quiet breathing, that we are going to be most concerned with. So, coming up, we're going to start talking a little bit about tidal volume and some calculations that we can do with it. And the reason that I want you to know tidal volume is because, especially if you're going into respiratory therapy, you're going to use the information on this page a lot. So we're going to talk about alveolar ventilation and how we can calculate it. Alveolar ventilation is going to be looking at how much air we move in and out of our lungs and how much of that air actually gets to the useful part of our lungs. But first, let's talk about something in the lungs called dead space. Now, the lungs are not hollow like a balloon. There's actually a lot of tissue inside of our lungs. And a lot of that tissue plays no role in gas exchange. During the self-study reading, you read about something called the conducting zone. Things like the larger bronchi and the larger bronchioles. So things that move air but play no role in gas exchange. So when we're talking about inhaling and exhaling, just because air is moving into your lungs doesn't mean that it's actually getting used. And how do we calculate dead space? Well, on average, it's 1 milliliter per pound of body weight. So if you weigh 150 pounds, then you have 150 milliliters of dead space. Let's see why that's important. 2 equations here to know. The first is called minute ventilation. Minute ventilation, MV, is equal to breathing rate, how many breaths per minute, times tidal volume, how much air is moved in or out of your lungs per minute. Now I'm going to let that sink in for a minute and see, does that sound at all familiar? Minute ventilation is the amount of air moved in or out of your lungs in 1 minute. Breathing rate is the number of breaths per minute. Tidal volume, I think I might have just misspoken a moment ago. Tidal volume, like I said on the previous slide, is the volume of air moved in or out of your lungs per breath. I think I may have said per minute a moment ago. But tidal volume is the amount of air moved in or out of your lungs per breath. So does this equation seem at all familiar? Well, it might sound a little bit like cardiac output is equal to heart rate times stroke volume. And it's very, very similar. It's just looking at the lungs and air instead of looking at the heart and blood. So one more time, just to make sure that me saying something incorrect a moment ago doesn't sink in. Minute ventilation is the amount of air moved in or out of your lungs in 1 minute. And it's found by breathing rate, the number of breaths per minute, times tidal volume, the amount of air moved in or out of your lungs in 1 breath. But really a better equation, a better measurement of how effective your breathing is something called the alveolar ventilation rate, AVR. Now the alveolar ventilation rate is this equation down here. AVR is equal to breathing rate, VR, times tidal volume minus dead space. Why is that important? Because here in the parentheses, tidal volume minus dead space, that tells us don't just look at the air going into your lungs. Look at the air making it to the gas exchanging portion of your lungs. Look at the air that's getting to the part of your lungs that actually does work in oxygenating and removing the carbon dioxide from your lungs and from your blood into your lungs. Now, if we do that, tidal volume minus dead space, and we look at the amount of air getting to the useful part of your lungs, and then times that by breathing rate, that tells us how much air is getting to the useful part of your lungs per minute. And that's a much better measure of how well your lungs are functioning versus minute ventilation. Now let's change gears, take a little breather for a minute, pause this video if you need to, because now we're going to move on to a completely different topic. We're going to look at properties of gases. And we're going to look at some more physics topics. And we're going to talk about partial pressure next. Now, Partial pressure is something we're going to mention a lot the rest of this chapter. Partial pressure is the contribution of a gas to the pressure of a mix of gases. I'll say that again. Partial pressure is the contribution of a gas to the pressure of a mix of gases. So let me see if I can explain this, and it'll make more sense a little later on. If you were to walk outside and you have the air around you, the air is actually made up of many different gases. I believe either later today or the next lecture we will see which gases it is, but it's actually several different gases. Some of it is oxygen, some of it is nitrogen, some of it is carbon dioxide. There's several different gases. And each of those gases has a pressure of its own. But when we mix all of those gases together, they add their pressures. We say we add their partial pressures together, and what we get is 760 mmHg, atmospheric pressure. So when we have a mix of gases and it has a pressure of its own, each of its components is contributing to that pressure. And the contribution of a gas is its partial pressure. So, for example, when we start talking about oxygen over the next few lectures, instead of just seeing oxygen, we're going to see PO2. And that's read as the partial pressure of oxygen. Or we're going to see PCO2. And that's going to be read as the partial pressure of carbon dioxide. What that means is we know there are other gases. We are specifically talking about oxygen right now. Or we know there are other gases, but we are particularly talking about the carbon dioxide right now. So the PO2 is just talking about the pressure of a specific gas when other gases are also involved. Now we're going to talk about something called Dalton's law. Dalton's law says that the total pressure of a mix of gases is equal to the sum of all of the partial pressures of the component gases. I'll say that again. The total pressure of a mix of gases is equal to the sum of the partial pressures of all of the component gases. So for example, when we look at all of the different gases of the atmosphere, they're all going to have a partial pressure. But if we add all of those partial pressures together, we should get 760 mmHg. Now, the higher in altitude we go, as we talked about in the previous lecture, there's less atmosphere above you. So there's going to be less atmospheric pressure. That 760 is going to be lower. And if there's less total pressure, then there's going to be less partial pressure for each of the gases. If there's less atmosphere above you, there is also less oxygen above you. There's less carbon dioxide and less nitrogen and less everything else, but there's less oxygen. That's why when someone goes climbing up a high enough mountain, they need to take supplemental oxygen with them because there is a lower partial pressure of oxygen at higher altitude. Now, the percent of a gas's contribution, its partial pressure, times the total pressure is how we get that partial pressure that we're talking about. So let's just say I have a gas and it's got a bunch of different gases in it, but I know that it's 20% oxygen. Well, if I measure the total pressure of that gas and I want to know how much oxygen there is, if I just said there was 20%, oxygen in that mix, then 20% times the pressure of the gas is the partial pressure of oxygen in that gas. So here's the composition of air on Earth. This is the atmosphere. Now, I, again, am not expecting you to know that there is 78.6% nitrogen. You don't need to know that. But I do want you to know that these four are the majority of our atmospheric gases. These four, nitrogen, oxygen, water vapor, and carbon dioxide, those are the big four. I want you to know those. I do not expect you to know the numbers of the percent or the partial pressure. You don't need to know those. But we're going to use this to demonstrate this bottom thing right here where it says the percent of a gas's contribution times its total pressure is equal to the partial pressure. Let's just look at the nitrogen. 78.6% of our atmosphere is nitrogen. That is by far the biggest component. And remember, our atmospheric pressure is 760. So if nitrogen is 78.6% of our atmosphere, 78.6 times 760, 78.6% times 760 is 597. Oxygen is 20.9% of our atmosphere. 20.9% times 760 is 159 mmHg. Water vapor, 0.5%, so half of 1%, times 760 is 3.7 mmHg. So that's how we find out the partial pressure of each of the gases. And if we add all of the partial pressures together, that's how we get our 760 mmHg. I want to talk about a disorder. I want to talk about oxygen toxicity. Oxygen toxicity. It is possible to breathe too much oxygen. And if you have me for Bio 137, you may have heard me go on and on about how oxygen is not good for us. Really, there is only one single reaction in our body that requires the oxygen that we breathe. That's actually the last part of the electron transport chain in cellular respiration. Other than that, oxygen is deadly. And as a matter of fact, oxygen is deadly to all living things. All living things develop a way to get rid of oxygen where it is not needed. Our cells have things called peroxisomes that help get rid of reactive oxygen. All cells have something to get rid of oxygen when it's somewhere that it doesn't need to be, because oxygen is not good. But luckily, it's only a problem above 2 atmospheres. That just means when we go somewhere where the pressure is so great that it is twice normal, that it is 2 times 760 mmHg. This is hard to find. We would have to go down deep, deep in a valley. We would have to go very, very deep. But the reason that oxygen is not good is because it's an electron hog. You may have heard that term if you ever took a chemistry class, or you may have even had your Bio 137 instructor use that term. All that means is on the periodic table, oxygen is really far to the right and it is really high up. That means that it is really electronegative. And things that are electronegative pull electrons towards themselves very strongly. Oxygen really pulls electrons towards itself, and it creates unpaired electrons. It will take an electron from someone and leave an unpaired electron floating around there. That's called a free radical. And free radicals cause all kinds of problems because they like to bind to things. But luckily, oxygen toxicity is not super common. Now I want to talk about external respiration versus internal respiration. External respiration is what occurs inside of our lungs. External respiration does not mean that it happens outside somewhere. External respiration is just the term for movement of gases between the lungs, between our alveoli and our blood. Oxygen moves from the alveoli, from our lungs, into our blood, and carbon dioxide moves from our blood into our lungs so that we can breathe it out. That's external respiration. Oxygen moves from the lungs to the blood. Carbon dioxide moves from the blood to the lungs. Now, this next part actually isn't going to make full sense most likely until the next lecture. So go ahead and write this down, but keep it handy so that when we have our next lecture, you can refer back to it. Even though oxygen and carbon dioxide are moving here during external respiration, there's some differences. Oxygen has a really steep partial pressure gradient. There's a lot of oxygen in the lungs versus not very much in the blood. And remember, everything likes to move from high to low pressure. Oxygen has a really steep gradient. Carbon dioxide's gradient isn't very steep at all. There's a lot of carbon dioxide in the blood. There's only slightly less carbon dioxide in the lungs. But it seems as though more oxygen should move since it has a steeper gradient, but that's not what happens. The same amount of oxygen moves from the lungs to the blood as carbon dioxide from the blood to the lungs. Even though carbon dioxide does not have as steep of a gradient as oxygen does, the same amount moves. And that's because carbon dioxide is a lot more soluble in water. What does that have to do with anything? Well, think back to when we were talking about capillary fluid exchange. Remember at the capillaries when things are moving in and out of the capillaries? It wasn't just oxygen and carbon dioxide and nutrients and waste moving. No, it was water that was moving. And all of that stuff was dissolved in water. So carbon dioxide is really soluble in water. And oxygen has a steeper partial pressure gradient, so it balances out. Equal amounts of carbon dioxide and water are exchanged. Now, like I said, that probably doesn't make a lot of sense yet. But when we get to our next lecture, refer back to that, because then it's going to make a lot more sense. Now, the thickness of the respiratory membrane is important. The respiratory membrane is where the gas exchange takes place. And the respiratory membrane is the wall of an alveolus plus the wall of a respiratory capillary. The alveoli are surrounded by capillaries because that's how we load and unload oxygen and carbon dioxide. So that oxygen and carbon dioxide has to cross the respiratory membrane either to get in or out of the blood. Now, think about what the wall of an alveolus is made of. Do you remember from Bio 137 or from the self-study part of this chapter? It's simple squamous epithelium. And what is the wall of a capillary made of? It is also simple squamous epithelium. What does that mean? Simple squamous epithelium just means one layer of really flat cells. So how thick is the respiratory membrane? It's 2 cell layers thick, and those cells are really, really thin because they're squamous. Stretch your memory back to Bio 137. What was the function of simple squamous epithelium? It makes diffusion really, really easy. So that's what that respiratory membrane is. The respiratory membrane is 2 really thin cell layers thick because we want that gas exchange to occur really easily. But sometimes that has scarring. Sometimes the respiratory membrane gets thickened. Sometimes there's a lot of mucus there. There's all kinds of things that could cause the respiratory membrane to be thicker. And that's, the thickness of the respiratory membrane is really important because the thicker it is, the harder it is for gas exchange to occur. Ventilation perfusion coupling. So ventilation, we've already said, that's air moving in and out of your lungs. Perfusion is talking about blood flow, the amount of blood arriving to some area of your body is the perfusion that that part of your body is getting. So here, when we're talking ventilation perfusion coupling, we're talking about how much air is getting into your alveoli and how much blood is getting to those capillaries surrounding the alveoli. We need those two things to match. If too much air is getting into the alveoli versus the amount of blood, well, then we're kind of being wasteful. We're not maximizing the oxygen that we could get out of that. And we're not maximizing the unloading of carbon dioxide that we can breathe out. At the same time, if we don't have enough perfusion, well, now we can't adequately unload carbon dioxide or pick up oxygen. So we need them to be matched. And we do that by having oxygen and carbon dioxide both play a role. Oxygen changes the diameter of the arterioles bringing blood into those respiratory capillaries. Carbon dioxide changes the diameter of the bronchioles bringing air into the alveoli. So let's look up here at the top. And by the way, this picture is on page 873 of your textbook. If there is decreased airflow, so if not enough air is getting into your alveoli, then there's going to be less oxygen making it into your blood vessels. And if less oxygen makes it into your blood vessels, we get vasoconstriction of those blood vessels. And if we get vasoconstriction, there's going to be decreased blood flow. And if we have decreased blood flow, now it's going to match the airflow that was coming in. If there was decreased airflow, now we've matched that with decreased blood flow so that the air and the blood match. On the other hand, if there's increased airflow, the elevated oxygen in your blood vessels causes vasodilation. Now we have more blood coming in to match with the increased airflow. So that's how oxygen plays a role. And at the same time, carbon dioxide is playing a role. If there's decreased blood flow, that's going to lower the amount of PCO2, the carbon dioxide, making it into the alveoli. So we get constriction of the bronchioles, which causes decreased airflow. Now the airflow has matched with the blood flow. And over here, if there is increased blood flow, now there's more CO2 in the alveoli. We get dilation of those bronchioles. There's more airflow to match with the more blood flow. Up at the top is what does oxygen do. Down at the bottom is what does carbon dioxide do. Internal respiration. So this is what happens between the tissues and the blood. So we've picked up the oxygen and dropped off the carbon dioxide at the lungs during external respiration. Now we're going to circulate that blood to the tissues. We get to the capillaries in the tissues. And now we're going to unload that oxygen to the tissues and pick up waste carbon dioxide to carry away. Internal respiration is just movement of gas between the tissues and the blood. And again, This happens during capillary fluid exchange, which we saw back when we were studying capillaries. Internal respiration, tissues and blood. External respiration, lungs and blood. But it's still exchange of oxygen and carbon dioxide. That will be where we stop for this lecture. I know this was a long one, and unfortunately the next one probably going to be long as well. Now, next one I might end up breaking into 2 lectures so it's not so hard on you, but we are going to start talking about partial pressures, and we're going to start looking at the mechanics of how internal and external respiration actually work. And we might start talking about how oxygen and carbon dioxide are carried in your blood. All right, I will talk to you next time.